Hello everyone and welcome to this Nordic Tech webinar. Today's topic is, as you can see, the industry's most compact power management solution. Introducing the industry's most compact power management solution, where we'll be talking about the new PMIC that we launched 2 weeks ago. My name is Robin M. Saltnes. I'm a product marketing engineer here at Nordic Semiconductor, and I will be the host of this webinar and read all your questions and monitor chat. The main speaker is Geir Kjosavik. He's our product manager for power management, also from Nordic Semiconductor, of course. And you can say a quick hello. I put you on the camera.
Hi there.
I'll let you continue shortly. But first, I'll go through some practicalities. The webinar will last for about 1 hour, consisting of approximately 45 minutes presentation with 15 minutes for Q&A. We encourage everyone to ask questions in the question box on the top right-hand corner of the webinar window. All questions asked in this box are anonymous. Questions from the chat will, as a general rule, not be answered during the presentation. If you have more questions, or if your question is not answered during the Q&A session, you are welcome to create a ticket on DevZone to get answers directly from our dedicated technical support team. And also, a recording of the webinar will be made available on our webinar page, along with the presentation after completion. Then I'll just have to hand the word back over to you, Geir, and take it away.
All right. Thank you, Robin. Hello, everybody. I'm going to start this presentation by just telling a little story. So I started in the semiconductor industry in the mid-90s, and my first job was to be a part of a team that introduced an 8-bit microcontrollers with 1K of flash memory that ran at 8 megahertz. At that time, MCUs or microcontrollers were relatively exotic things, and I remember how we were completely baffled by an industry report that projected that in the not too distant future, an average home in the industrialized world would contain as much as 250 microcontrollers. Now, today, almost 30 years later, we're way past that. And the amount of processing power and connectivity options that exist in everyday use items is just mind-blowing. We come to the point where we're stuffing electronics in the form of crafty PCBs into all kinds of weird form factors, big and small. And today, we're going to address the small ones that we carry around. Some people may have been asking themselves why Nordic is getting into PMICs or power management ICs. Well, there's more than one answer to that. I'd like to argue that this is not a new thing for us. Nordic has done this for a while, as their product lines all contain power management in some form. We have been doing highly efficient DC-DC converters with the ability to control multiple power rails for a while. However, in 28 nanometer technology, where we are today, you can only get so far, even with the best analog design engineers on the planet, which, by the way, I would argue that we have quite a few of. But unfortunately, laws of physics are limiting the maximum performance, especially when it comes to efficiency. Process nodes like 180 nanometers, which you can use when you're not sharing silicon area with multiple ARM processors and high-density flash memories, give us a lot more freedom to achieve better performance and allows us to include the battery charger. And the battery charger is important because wireless products, as if you think about it, are wireless for a reason. They often get carried around. And things that get carried around need to carry with them the energy reserves in the form of a battery, and often that battery is rechargeable. So we've helped thousands of customers connect their small things to the internet. And going forward, we're also now going to help them charge and power the same things while keeping them small And that is a theme for this presentation. We are, with this product, aiming for anything small and rechargeable, or at least anything with a small rechargeable battery. Like these things. Designing most of these products, if you happen to be on a team that does that, you know that this is an exercise in packing as many features as you can into a small form factor enclosure. And every cubic millimeter counts. But even those of you who aren't space constrained will benefit from this, the features of this device that I'm going to be presenting to you, as long as your product is using a small battery. The highlights of the NPM 1100 is, well, the word small is going to be repeated a lot of times during this presentation. Only 23 millimeters of PCB area, including passive components. Now there are solutions that are smaller than that, but in the end of the day, they don't result in a smaller product. And why that is, we will keep getting back to. We have a linear charger in this product that can charge a lithium ion or lithium polymer battery up to 400 milliamps. And then there are two power outputs, one unregulated and one regulated, very highly efficient buck DC-DC converter. If we move to the block diagram, which is a simplified block diagram showing the most important parts of the device, I'm going to just point out a few really important features. First of all, full power path management. This is pretty common with power management ICs like this. It means that when the device is plugged into USB, it can draw 500 milliamps from the USB bus, and out of that, what is not used by the application, what is left over when the application, which gets priority, has taken its part of the current, what is left over can be used to charge the battery pack, up to 400 milliamps, but this is configurable. When USB is unplugged during battery charging and USB powering the whole application, the current flowing into the battery is immediately reversed from going in to going out, and the battery changes its role from being charged to powering the system seamlessly with no glitches. There are two power rails, one unregulated, which when powered from USB will be at 5 volts, and when not powered from USB will be at whatever the battery is at. And then there is a regulated power rail that we're going to take a look at as well. The battery charger supports the two most popular rechargeable lithium battery chemistries. So it can be configured with a 4.1 or 4.2 volt termination voltage. The configuration of this device is done by strapping pins, and also the charge current is selected by a resistor. So there is no software needed to configure this device. Everything is done board layout time. It can charge a 400 milliamp battery up to 1C. 1C means that the charging current in milliamps matches the battery capacity in milliamp hours. Obviously, if the battery can take 2C of charging, which some can, or you're not concerned with battery longevity and wishes to charge at 2C, because there's a benefit to that. Obviously, the maximum supported battery size will be 200 milliamp hours. But I assume that most of you who design small rechargeable applications will be charging at 1C. GEITA compliance means that charging current is reduced when the battery has low charge, high charge, is cold or warm. This is a regulatory specification that most power management ICs follow. And these are necessary to prevent permanent degradation to the battery. There is a third input on the battery charger that connects to an NTC thermistor present in most battery packs. And this is used to measure the temperature of the battery. Some battery packs do not have this, and our product can still be used. The datasheet will tell you what to do with this input if it's not connected to an NTC. Also, the charger has thermal protection, which is not to protect the battery, but protect itself. 400 milliamps of linear charger isn't a whole lot, but there is always the risk for devices where the components have poor thermal dissipation, that the chip could overheat. And the mechanisms that prevents it from doing that works as follows. If it reaches a certain critical temperature, it will shut off charging. It will allow itself to cool down slightly, and then it will continue with a reduced charging current. The power supply part, as I said, is a highly efficient buck DC-DC converter. And it can supply 150 milliamps to the application. And the 92% efficiency really is big in class if you compare us with similar products. And this is important, and we will get back to that. So high efficiency means that less current is drawn from the battery than is input to the system. If you have a 4-volt input from the battery and you are supplying 1.8 volts to the application, that means that if the application is drawing 150 milliamps, then the battery only needs to supply 75 milliamps because it's supplying at a higher voltage. So it's about 10% of the power that gets lost in that DC-DC converter. The way we achieve this really high efficiency is 2 operating modes: PWM for high currents and hysteretic mode for low currents. The regulator automatically switches at a certain threshold between the 2 modes to always be choosing the one that gives the highest efficiency. Hysteretic mode can, since it is kind of broadband in frequency, can, in some cases, unlikely but possible, interfere with radio communication. The way that is solved is that the host can force the PMIC into PWM mode during communication to mitigate any interference from the DC-DC converter operating in hysteretic mode. There are 4 selectable voltages, and you will have to choose one of these 4, which again are selected through 2 pins on the device. So you binary decode them either 00, 0110, or 11, and then you get one of these 4 voltages by strapping pins high or low. And then 150 milliamp current limit, which for these kind of applications should be more than sufficient. Yes, well, the recurring theme of small becomes apparent when we look at the package. The device is available in a wafer level chip scale package measuring 2.1 by 2.1 millimeters. The stacking height is about half a millimeter, and it has what has now become fairly standard ball pitch of 0.4 millimeters. And we've tried to keep the number of passive components to a minimum to make this as small as possible, but that leads us to some interesting compromises that can be made between size and performance. Depending on what is important to you, you can choose a design that is optimized for high DC-DC efficiency, or you can choose one that's optimized for low PCB footprint. A white paper on our website explains the inductor trade-offs that you must do in order to achieve either or. If you go with this big inductor, the DC-DC will operate more efficiently, but it is almost as big as the chip itself. And by dramatically reducing the size of the inductor, you can achieve same great performance with just a little bit of drop in DC-DC efficiency. Now, as will become apparent later in the presentation, spending the extra component volume or space to achieve higher efficiency often pays off. Because if maximum battery life in a small enclosure is important to you, spending components, investing in components that give higher efficiency is much more economical than putting in a bigger battery, both from a dollar standpoint or from a sheer volume space point of view. The performance optimized design you can check out through the NPM 1100 evaluation kit. As you see here on this board, you see that exact component layout that that I showed you in the previous slide. So this development kit allows you to connect to any system that you want to load with this, or any battery that you want to charge with it, including obviously Nordic development kits for our short-range Bluetooth devices. Since we don't know what configurations our customers will be using, we have put in a number of dip switches so that the selections or the configurations that are usually done as you lay out the board now can be altered through these dip switches. This kit is in stock with our local distributor, and you can buy one today and evaluate the device if you think it is a potential fit for your application. It also works with our power profiler kit, so you can really check out the power consumption here and verify the claims that I made on efficiency. Because efficiency is so important, and in the next slides, we're going to be discussing how these are basically the same thing, just coming from two different directions. All right, so looking at the efficiency here, in order to do that, I pulled in two curves from a data sheet, the best case and the worst case curves. The best case is when the regulator doesn't have to regulate all the way down, but from battery voltage down to 3 volts. In that case, it actually stays north of 90% efficiency all the way down to about 40 microamps. And if you wonder what this little dip in efficiency up here is, and why the curve is double, now this is entering and exiting out of PWM mode, or the transition between hysteretic and PWM modes in both directions. So this is where this magic happens, that the DC-DC converter goes from supplying current in one mode to the other, because in order to retain the efficiency across the entire range of current. So the problem is that getting maximum battery life in a small enclosure really is a three-dimensional puzzle, literally, but also figuratively. because you have to balance multiple interdependent parameters to maximize results that are kind of mutually exclusive. It's really hard. And I assume that we have people in the audience that have gone through this exercise in designing small products. How do we get everything in there and still retain the battery life that is going to give our users or our end customers a good user experience? But it all boils down to the simple fact that high system efficiency inherently means small size. Because overcoming efficiency using a bigger battery just takes up a lot more space than the chip technology needed to achieve the high efficiency. So investing in high efficiency always pays off. It's the best investment you can do. And we're going to just unpack that in the next slides so that you can see some numbers and really understand where this is coming from. All right, example, fitness tracker. So in this example, the designers have chosen a really small PMIC and to operate or charge and power the application from a 151 milliamp hour battery. This is a typical battery size for this kind of product. This fitness tracker has a minimum time between each charge of 48 hours. Now, that is with normal use where the display is used very little. It is only active when the customer is actually looking at it. So it's not lit for most of the time. And with that, if we take the display out of the equation, which we really can, we see that with 150 milliamp hour battery and 48 hours between charge, we're looking at approximately 3.1 milliamps of current being supplied to the electronics inside the fitness tracker, which runs at 1.8 volts. The PMIC they have chosen is a very obvious choice when you're making small things. It's the TI-BQ25150. It is one of the absolute most compact solutions on the market, as I'm going to show you. And we see a lot of these kind of products using that PMIC from TI, or one that is related. They have a number of these very similar in features and with the same extremely compact design. The redesign challenge for this company is to increase the battery life in the next version of the product by a day and a half, and now go from 48 hours to 84 hours. That is a challenge. And they really want to do that without making the product bigger. If they have to, well, they'll have to beat the bullet on the tooling and everything, but there's a limit to how big they feel they can make the product before it becomes unattractive to their customers. Customers like things that are small and thin, especially when you're going to wear them on your body for 24 hours a day. So let's look at some options of achieving that long battery life with two different approaches. So the first is to consider a different PMIC. Now, the BQ25150 is really, really small and inexpensive. It's only 12 square millimeters of board space required to do everything that this product needs to do. If they go with the NPM 1100, since it has a DC-DC converter, it's both, I mean, it's slightly more expensive. It is quite a bit bigger in terms of the total board space required. And then there's a cost of that inductor. And this is inevitable. If you're going to go with a DC-DC converter, you have to put an inductor on the board, and that is an investment in both board space or volume, and then also sheer money. So that is the investment. However, the Nordic PMIC, as compared to the BQ25150, is going to give this company what they want. They will get past the 84 hours and actually with some margin using our PMIC. The reason for that is that the BQ25150 having a linear dropout regulator is unfortunately horribly inefficient, which is just what happens when you take 3.7 volts and you regulate it down to 1.8 volts, and you just shave off that power difference in terms of heat. If you install a DC-DC converter and you do the same thing, you see that the power being drawn from the battery is much lower, because now you have a power conversion component instead of something that just regulates down. So just by putting that efficiency in, you get a higher battery life, and you get the battery life that they're targeting. Now, so we're there where we can achieve the 80% longer battery life, but there is a cost, obviously, as we saw in the previous slide. It's 13 cents, and I'm talking about 1,000 piece prices now that are official, so I can to make a comparison that works for everybody. So 13 cents extra component cost and about 11 cubic millimeters of extra volume. We're now assuming they're using a flex PCB, which takes up, which has virtually zero thickness. So that is the investment in space and money. All right. So with that approach on the table, and with those numbers hashed out, what does the alternative look like? Which is investing in a bigger battery, or what I call throwing milliamp hours at the problem. Okay, let's unpack this as well. I have looked at the entire portfolio of batteries available through 2 distributors to determine the cost of increasing this battery size and to achieve 80% longer battery life. The interesting thing with batteries is that each milliamp hours quickly gets a lot cheaper as you go up in battery size. Actually, the cost of increasing battery life with a certain percentage is pretty flat and is pretty independent of capacity. But as my calculations show here, looking at these wide range of battery models being available, I've found that the cost of increasing the battery to achieve that 87-hour battery life is about 31 cents. And it's not dramatic. I think it is clearly puts the NPM 1100 makes it favorable, but there may be reasons why you would eat those extra cents and just stay with the battery that you have. And that's fine. There's a cost of redesigning electronics as well. However, in a small product like this, as I've already alluded to, the cost of the battery in dollars is not the only cost. There is also a cost to getting things to fit in there in terms of volume. And here, the volume per capacity is pretty flat. If you are doubling your capacity, you're doubling the size of the battery, pretty much like that. And at least if you get up in 200 to 300 milliamps and beyond that, the scales really linearly. The reason why the small batteries are less efficient volume-wise is that these things that are in there, a safety chip, a NTC thermistor, connections, cell terminals, all these kind of things, take up the same volume in a small battery as in a big one. So they become a bigger part of the whole volume. But as soon as you move out beyond 200 milliamps, that doesn't even register. So here, increasing the battery capacity by about 80% to get to the 87-hour battery life or 84-hour battery life is a whopping 960 cubic millimeters. And if you're really space constrained, that staying with the linear dropout regulator and increasing the battery size is completely off the table. It becomes very obvious that investing in higher efficiency is the way to go. And this is what you will usually see. The big cost here is volume, but for some people also the extra cost in dollars will be unpalatable for the engineering exercise that we're going through. So efficiency really is king. And I just keep repeating myself here, invest in efficiency before you invest in a bigger battery, because that's the smartest way to get more stuff and more things done and longer battery life. So what about ship mode? Anybody who's already read our data sheet may have picked up on the fact that our ship mode numbers are much higher than TI. So I want to address that. The engineers at TI did a really good job and probably put a lot of effort into achieving a ship mode current of 10 nanoamps. So what is ship mode? Well, ship mode is an ultra-low power state that allows for long shelf life without depleting the battery. So let me just explain that first. When somebody manufactures a product, it can take many months between the product is manufactured until the end user actually buys it, unboxes it, and starts using it. In order, and it's very important that during that time that the battery does not drain completely for two reasons. If it drains completely, it can go below the critical low voltage, which means that the battery is either permanently degraded or is completely ruined, which certainly is not what the end user would want to happen to a product before he takes it out of the box. Secondly, if most end users are like me, when you unbox a product, you will want to play with it and check it out at once. It makes for a much better out-of-the-box experience than if your newly purchased gadget needs an hour of charging time before you can even do anything with it. So there's a number of reasons. And also for air shipments, it is required that the product goes into some kind of ultra low power state where the battery drain is kept to a minimum. So this is important. However, the 10 nanoamps that TI, as I'm sure, put a lot of engineering effort into achieving, looks then incredibly impressive compared to our 470 nanoamps. And unless you have looked at what this really means, it could be a turnoff. But I would argue that the sleep mode numbers, which gives TIs a lot of bragging rights, is almost a little bit like megapixels was in the early age of the digital camera. It is an impressive number that gets thrown out that for some unsuspecting users could translate into good quality. And in this case, good quality pictures. A lot of megapixels must be good pictures. Well, we know that now. It isn't like that. And it's the same thing with ship mode. The number is impressive, but it isn't really significant. It has very little relevance in real life. The thing is that this battery, this 151 milliamp hour battery in the fitness tracker, has about 6.3 microamps of total of constant self-discharge current. This is based on a typical lithium battery losing 3 percentage points of state of charge every month. And if you do the math, that equates to 6.3 microamps of constant self-discharge current. So when you add that to the nanoamps, the difference becomes much smaller. And it's still there, but it's now a lot smaller. And if you do the math on what this means in a real life scenario, it becomes even less significant. The way a lot of manufacturers, and you know this if you have products that contain rechargeable batteries, is to charge the battery to about 50%, where lithium batteries thrive in storage, and then enable ship mode, box it, and ship it off. In the case that it takes 6 months between manufacturing until somebody buys it and unboxes it, I've done the math on what the differences between these two ship mode currents actually means to the end user. So the product that had the TI chip, when it's opened, will have retained 31.9% state of charge, whereas if you use our product that has a slightly higher ship mode current, will have retained 30.6% state of charge. With that, I'd argue it's hardly significant. And we just found that investing the engineering effort it is to get even close to the TI numbers were not worth it. We'd rather spend those on achieving best-in-class efficiency when the PMIC is actually operating and actually supplying current to a live product. So that's where that is coming from. All right, that is everything I was going to tell you about the NPM 1100. But now that we are officially a PMIC company here at Nordic, obviously there's going to be more happening. So let me just walk you through quickly some real simple highlights of where we are going and what direction we're taking this product line. So we just gave you a product for the really, really small applications with small batteries and sometimes very small enclosures. Going forward, there's a bunch of products like the speaker, for example, that is just where the NPM 1100 is not very suitable because it has a bigger battery, it needs more power, and has multiple power rails, so that is coming. PMICs that support bigger batteries and more supply rails is already in design. Then another thing that we're going to do is looking at how PMICs work and looking at them from a system architecture's perspective. We have found some unique system management features that we think are missing on PMICs that are available today, and we're going to be putting them on there. And I can promise you that these will be incredibly useful. And when you see the first product specification of our next product, you will be thinking to yourself that why didn't anybody else think of putting these features on a PMIC? Because they're really cool and extremely useful, and are just going to make it a lot easier and less expensive to design well-functioning products. And those coin cell batteries at the bottom are kind of giving away my third bullet point for our roadmap, and that is establishing a PMIC that can ensure battery life, long battery life for disposable batteries, either if it's coin cell or alkaline or whatever. a great deal of you, I assume, are designing products that have disposable batteries, because in a lot of cases that makes a lot of sense. Rechargeable can be a nuisance for a lot of products, and it just doesn't really make sense. But if you are designing a product with a disposable battery, well, first of all, you would need not only a buck converter, but you would most likely also be needing a boost converter. And you would not be willing to pay for a battery charger, because that part of the circuit is just not being used. So that is coming too. Our goal is to be able to cater to all our customers designing wireless products that have some kind of battery built in. Now, in order for us to make really cool products, we need to know what problems we can solve for you guys using our technology and our expertise in this area. So apart from talking to as many of you as possible, which is a very good but somewhat inefficient way to gather a lot of data, we have created a survey. And if you think that you have some good ideas, or you have some specific needs that you would like to see in a PMIC, I would encourage you to take the survey. It takes very short time. There are some quick questions on what kind of batteries you're using and what kind of capacities, but there are also some free text fields where you can articulate what you would really like to see in a PMIC that would make your life easier and make your product better. And I can't promise anything, but the chances are that if enough people are asking for something that makes a lot of sense to put in a PMIC, there's a chance that we will include exactly that. So, and here, no wish on that wish list is a stupid wish. We'll anything's possible. And we'd really like to hear from you in the audience on what you would like to see in our roadmap, and what we can help you out with on your power management side going forward. So with that, I'm going to just wrap this up and summarize what we just talked about. And by now, you should have gathered that this product is about small size, charging small batteries, and supplying that battery energy with extremely high efficiency to the rest of the system. And this is important because, well, bigger batteries are not an option. That's not the way to increase your battery life or times between charging. And just to summarize the whole story, and the fact that Nordic is going into this product space, which I'm really excited about, and I hope you are equally excited about, is just thinking about what's happening here. And that is that Nordic, who has helped millions of devices, small devices, connect to the internet, is now also at the same time helping you charge and power these small things while keeping them small. So making you able to put more features in your next version, your next model, without making it bigger. That is what we want to help you out with. So thank you all a lot for listening to me.
Yes, that's all we had for you today. Thanks for attending this Nordic Tech webinar. For more webinars, you can go to nordicsemi.com/webinars to register for upcoming webinars. And I'll just wish you all a nice day.